Let us start this lecture with a thought process, explore and experience the very essence of human life. It is very difficult to get human life as per our scripture, right? But we do waste the time for, behaving like an animal. So, therefore, we need to experience that essence of human life, what animal cannot. Now we recall what we had learned in the last lecture. In the last lecture, if you look at, we basically looked at how to determine the adiabatic flame temperature. In that case, what we did, we basically were knowing that what will be the product composition, right? Of course, reactants should be known to you. What will be the how many number of moles of fuel, how many numbers of oxidizer, right? That will be given to you. But product you won't be knowing, right? But here we are assuming, oh, it is going to the stoichiometrically or it is going to the lean and lead. Product is known. That means number of moles of each constituent of the product are known to you. But in real situation it won't be, right? Are you getting? For that, what we will have to do, we will have to look at, equilibrium compositions. Now question arises, we need to calculate equilibrium compositions, right? And if you do not know the equilibrium composition, you cannot calculate accurately the adiabatic temperature, flame temperature, right? And if you do not know the adiabatic flame temperature, you cannot really calculate the equilibrium composition, right? So we will see as we go along. Let us now look at basically chemical equilibrium. We will consider a chamber, right, which contains hydrogen and oxygen, right? It will be at a certain mixture, a certain what you call ratio, fuel air ratio. Hydrogen is fuel, oxygen is your oxidizer. Now, if it is there, let us say at 298 Kelvin, what will be happening? Is it some reaction will be going on or not? Is it some reaction will be going? For example, this room, imagine, right, that contains hydrogen and oxygen and mixed properly with certain, let us say, stoichiometric ratio. That means where combustion can take place, right? But it is at 298 Kelvin. What will happen? There will be some reaction or not? But there might be, okay? Because the molecules might be getting bombarded, they will be colliding each other, they might be breaking, they might be coming, they might not be, but that is not really very much. But if you raise the temperature, let us say to 1000 Kelvin, what will happen? There will be some reaction which will be taken. That means hydrogen will be reacting with oxygen, and we are saying it will go to the water, right? Let us say 2 moles of hydrogen reacting with 1 mole of oxygen, it is going to the 2 moles of water. But is it really will be occurring this way? Need not to be. It can also happen, right? The water will be decomposed into oxygen and hydrogen, right? It can also take in the reverse process, right? One we can say forward reaction. If I say forward reaction, right, Kf I am saying, right, K means basically reaction rate constant, you can say, and backward reaction, this is arrow in the opposite direction you will be taking. Now let us say at 1000 Kelvin it is being raised, now some reaction is occurring, then the products are being formed, and as you goes on, measuring this hydrogen, oxygen and water, let us say for example, right, then what will be happening after a certain time, that the concentration of hydrogen, oxygen and water, if we are measuring, will be remaining constant, isn't it? They won't be change after a certain time, right? Then we call it as a reach a equilibrium, right? But question arises, is it at the equilibrium only water, hydrogen, oxygen will be there, or only water will be there? all three will be there. But is there, apart from that, is there any other species will be there likely to occur, right? So, what are those species one can think of? Any idea? OH, maybe O, right, H, all those things can be there, right. So, the product, if you look at, it will be hydrogen, oxygen, water, OH, H, O, and some other things as well, like, okay. Now, question is it like the equilibrium when you say it is basically reaction is going on or not, or reaction is stopped? It will be going on, right. In this case, what will be happening? Like if we will consider, I will go back to the simple example of let us say 2 moles of hydrogen reacting with 1 mole of oxygen going to the 2 moles of water. That means there will be forward reaction and also there will be backward reaction even at equilibrium, but the forward reaction rate will be same as that of the backward reaction rate, yes or no, right. So, then we call it as a equilibrium, right. That means it is statically equilibrium or dynamically? It is basically dynamically, it is all is going on, only the forward reaction is same as the backward reactions, right. So, that will be one. Let us take an example like methane. 1 mole of methane is reacting with 2 moles of air and going to the product of carbon dioxide, 1 mole of carbon dioxide, 2 moles of water, and of course 7.52 moles of nitrogen, right. And of course, these are the things what we generally write, right. But however, we can say that backward it also will be reacting, like product will be converted into the reactants, right, in a backward direction also. So, apart from these stable species like carbon dioxide, water and nitrogen are stable species, there will be also other species which will be there. What are those? Any idea? If you look at, it will be CO, right, hydrogen, it can be CS3, CS2, CHO, CO, oxygen, OH, H, O, NO, NO2 and several other species which I have not listed, like it will be several species, right. And keep in mind that at equilibrium we need to find out what are these mole fractions or the mass fraction of this species at the equilibrium. For example, methane air system if you are handling is very small. I have only jotted down few of them, it may be some more number of species, it is very difficult, right. Now, what I had told you earlier that this is occurring basically when the pressure and temperature is not changing, right. That means the chemical composition will remain same provided the temperature and pressure, in this case let us say P, I can say 1 atmosphere pressure, temperature is 1000 Kelvin, right, that is not changing. If I change, right, that either temperature or the pressure, then what will happen to the equilibrium composition? Will it equilibrium maintain? Equilibrium will be changing, right. That means any change in this, either one of them will have a change in the composition, right. So, that is very important, you should keep in mind. In order to find the mole fraction of equilibrium products at certain pressure, we need to invoke chemical equilibrium conditions. So, what are those conditions? We need to look at it, right. So, as I told that equilibrium basically will tell you the extent of reaction or a process whatever is taking place, right. And at equilibrium, right, and it will be telling basically how much, it will not be telling you the rate of reaction, right, it will be telling extent of the reaction is taking place or the process, how far it can go to attain the equilibrium. So, as I told that that at equilibrium reactant and product concentration remain constant, right, it will not change unless otherwise there is a change in temperature or the pressure, right, or there might be also some change whenever suppose some reactant will increase, suppose some reaction is going on, let us say hydrogen oxygen, you have added little more hydrogen, okay. Let us say in a chamber it is a reaction is going on equilibrium something, then you add more hydrogen, that means concentration you have changed, there will be also change in the composition, right. Even you change the volume, right, then also it will be changing the equilibrium composition, right. So, at the macroscopic level what is happening? It is remaining unchanged, means what? At equilibrium composition is not changing at the macroscopic level. But if you look at microscopic level, what is happening? Is it changing or not? Something is happening or not, right? That means reaction goes on, it is basically known as dynamic equilibrium, right. But however, how then it is happening, the macroscopic level is not changing, because the rate of forward reaction is same as the rate of backward reaction. That means the reaction rate of the reactants is equal to reaction rate of the product, okay, at equilibrium. Are you getting? So, that is the very important thing you should keep in mind. Now, rate of reaction means what? Basically change in moles of species per unit time per unit volume, that is moles per second meter cube, right. Now, when you talk about this thing, but we will have to evaluate this reaction rate quantitatively, right. Then for that we will have to use basically the law of mass action, which was given by two Norwegian chemists, Gullberg and Weiss, in 1867, right. Because we are interested to find out, right, a quantitative relationship between the reactant and product. For that we need to invoke the reaction rate. So, therefore, we will have to find out, right. So, law of mass action states that reaction rate of a chemical species is proportional to the product of concentration of the participating chemical species, right, where each concentration, right, is raised to the power of to the corresponding stoichiometric coefficient in a chemical reaction, right. And this you must have studied in your +2 level, right. We are using it again and again. I will be invoking law of mass action, right, in whenever we are dealing with chemical kinetics, okay. This is a very important one which you need to understand and keep in mind. So, let us consider an arbitrary bimolecular reactions, right. For example, like A moles of species A means capital, right, is reacting with B moles of species capital B going to the C moles of species C and D moles of species D, right. Now, I want to write down this law of mass action for this. What it would be then? Any idea? This will be reaction rate is basically of AB, if I take, is proportional to Ca concentration A power to the small a, concentration of B power to the small b, and this proportionality constant what you call basically Kf, that is forward reaction constant. You can, if you look at according to law of mass action, right, Rr is proportional to Caa and Cbb, right, and then this is equal to basically like that. This Kf is the forward reaction rate constant or the specific reaction rate constant, people say that. And similarly, reaction rate of Cd, like when it is getting to backward direction, then Rr is proportional to CCC and CDD, right, and Kb is backward reaction rate constant, right. So, at equilibrium, what is that? RAB is equal to RRCD, right. So, therefore, we can say basically from here, right, I can say Kf and using this relationship here, right, Kf CAA CBB is equal to Kb CC and CD coefficient basically d, small d, right. Then I can write down this, we can write down Cc power to the C, Cd power to the small d divided by Ca power to the A and Cb power to B is equal to Kf by Kb is nothing but Kc, and this Kc is what? Equilibrium constant, right. This is the constant based on the concentration of the species, right. So, now we will have to see how we will handle it and what are the things, right, about this equilibrium constant. If I know these values, right, Kc, if I know this Ca and Cb, then I can find out basically Cc and Cd, that is the requirement what we need to estimate, right, because we are basically interested to find out what will be the product, right, concentrations, and at the equilibrium what we will have to find out. So, we know that Kc is basically this term, right, and if you look at Kc is, let us say, very less, right. If it is a very small number, what does it mean? That means basically the more reactants are favored, that means the reactants in the equilibrium product will be more as compared to the actually the product species, right. But if Kc is very large, right, that means this will be, this portion, the product portion will be much larger than that of the reactant. So, therefore, products are favored. But if it is in between, that means reactant and products will be kind of thing will be there. So, that we will take an example maybe to see that little later on. But now let us look at basically concentration means the number of moles per unit volume, right. And I can write down this by for the ideal gas, because keep in mind that we will be using ideal gas for our combustion calculation for all the practical purposes, right. So, then that is nothing but your partial pressure away divided by RU T. RU is the universal gas constant, T is the temperature, right. Now, what I will do, I will, instead of this concentration, I can express in terms of partial pressure, right. So, then Kc would be basically Pc by RUT power to the C, Pd divided by RUT power to D, right, and that is in the numerator for the Kc, and denominator will be Pa RUT power to the A and PV RUT power to the B, right. I can segregate, that means write down this partial pressure of each species separately and temperature separately. So, that would be basically this term comes into picture, and this we call it as a basically known as Kp, right, equilibrium constant based on partial pressure, right, and RUT is C plus D minus A plus B, right, and that you can see. Now, we will be more interested to basically find out in terms of mole fraction, right. So, what we will do, we will now convert this into mole fraction, right. So, we know very well that right, mole fraction is Pa XA P. P is the pressure of the mixture, Pa, small pa is partial pressure of species A, right. Summation of partial pressure of small species will be equal to the total pressure, right. So, then we can write down basically here in this place I can write down Pc, then Xcc and Xbd divided by Xaa and Xbb. Of course, this P will come into picture in the same term. So, this I call it as a Kx. That means, if you know one of them, you can convert into other forms, right, equilibrium constant, 3 equilibrium constants being used, right. Let us consider an example of water gas shift reaction, right, a reaction which is being for producing hydrogen, right, because if you use in a reverse way, right, you can carbon monoxide reacting with the water going to the hydrogen and carbon dioxide, right, you can really and get that, and other way around, you want to produce the carbon monoxide, you can use that. Let us say this is a heat of reaction for this reaction, of course. Now, Kc, if I want to write down for this reaction, it will be Pc, right, this is a 1 mole. So, therefore, the like index is 1 and P water divided by PCO2 and P hydrogen and 1 by RUT, and keep in mind that this is all are 1 mole. So, therefore, this will be equal to 0, right, yes or no, right, and then right is equal to basically Kp, Kc is equal to Kp, okay. That means, it says when there is no change in number of moles during chemical reaction, then Kc is equal to Kp. Only for this condition, otherwise it will be different. Kc is not same as the Kp. Are you getting? So, let us take an example, right, and in this example basically ammonia is produced by Haber-Bosch process as per the following reaction. 1 moles of nitrogen reacting 3 moles of hydrogen getting into 2 moles of ammonia. You might be knowing this ammonia, is being used for the first time by these people, like being produced by Haber and Bosch separately, and right. So, at 1000 Kelvin equilibrium constant is Kc 0.0024, right, is given. Now, we need to determine equilibrium constant Kc for this reaction, right, like 1/3 mole of nitrogen reacting with 1 mole of hydrogen getting into product of 2/3 moles of ammonia, right. So, if you look at the reaction, we know that N2 plus 3S2 into 2NS3, right, and this is let us say reaction 1. I can write down Kc1 as CnS3 2 divided by Cn2 Cs2 3 is equal to 0.0024, and for reaction second reaction, right, that is 1/3 N2 plus S2 2/3 NS3, what will be Kc2 will be CnH3 2 by 3 divided by N2 1 by 3 and Cs2, right. If you look at, right, this is nothing but Kc1 power to the 1/3, isn't it? So, that will happens to be, that means Kc2 is equal to 0.0024 power to the 1/3 is equal to 0.13. In this case, if you look at, we can calculate very easily from the, if I know one of them, other thing. But what is the implication of this example is that Kc2 is greater than Kc1, yes or no, isn't it? Because this is 0.0024, this is 0.13. So, this is greater. That means, in this case what will be preferred is the products, right? Products are preferred or favored, right. Now, we will learn more about how to handle this equilibrium constants and how to calculate, because in this example it is given Kc, but now how I will know that we will have to see in the next lecture. We will stop over here. Thank you very much.